everybody. Welcome back to the Violent Universe. I see that there's 212 participants and quickly going up. So we'll see if we can go beyond that 300 participant capacity today. So like today, I mean, for those of you who come early, I usually start the class, I mean, not the class, the Zoom session about 10 minutes before the hour. And I usually post announcements that are just going on a cycle, and as well as videos that I find during the week. So this week I found this video about the first astronaut, first African-American astronaut. So I thought it was kind of cool, and I wanted to share it with you. So I do that. It's obviously optional. So for those of you who join in early, just something to keep you entertained while we start class. So yeah, the number of participants keeps going up, so we'll see. Let's see. So let me get started. Today we're going to talk about the universal laws of motion. So it's a little bit of a different class. Oh, I see that my displays are swapped. So let me, yep, that looks much better. All right, so just to answer a quick question, the notes that you guys take from your lecture and readings, you can use them while you're taking your open book midterms. Yes, that is correct. Only for the midterms, not for the quiz, not for the final, just for the midterms. You can use any notes that you have. All right, so let me give you just a very quick couple of announcements, just another reminder that there are no discussion sections this week. And yeah, that's it. So no discussion sections this week. Your first homework will be posted on Friday in the evening, Friday evening after class. Give me a couple of hours just to get it together and put it there. You'll be able to download it, work on it, and then when you have your discussion section next week, you bring your homework and then you'll go over the answers with your TAs. It's your opportunity to interact with your classmates, to interact with your TAs, ask any questions that you have. And then when it's all clear, people will put their notes away, and then you will have a quiz that consists of 2 questions out of the 10 to 15 questions from your homework. So I hope all of that is clear.
I will do it now. Right?
Sorry?
Oh, sorry.
All right. So yeah, so I will look at your questions in a second. Yeah, so I will repeat this announcement a couple of times just to make sure that everybody gets it. So forgive me for being repetitive. So let me look at your questions very quick. So I will give more detail because I'm getting a lot of questions about the midterms. I will give more detailed instructions about that later. Please bear with me because otherwise I will be repeating them every class. Discussion section start next week. Yes. All right, so it's very, very detailed questions about the quizzes and the exams. You can read it on your syllabus. The syllabus contains all the information that I'm actually saying right now. So let me just get started. And then at the very end of the class, you're more than welcome to stay. And I will finish today at 4:50. And then you can stay behind and you can ask me all the questions about midterms and quizzes and all that. And I'll be more than happy to answer them. So, all right, so today, in today's lecture, it's going to be a little different from the rest of the classes that we're going to have, in that we're not going to be talking about astronomy per se. This is going to be our most like physics class, because I want to introduce a bunch of physics concepts that we will be using throughout the class. Just the definitions, and so it might be a little more dry than the rest of the class, not so many pretty pictures, if you will, but it's necessary. We need to all be on the same page. And actually, before I get into that, I just wanted to give one more announcement, which, you know, should be a given, but it's not a bad thing to repeat it. And I just want to make sure that everybody understands that this class, Physics 6, is meant to be a safe place, a safe space for everyone, for every student, regardless of your background, regardless of wherever you're coming from, whatever your, you know, all those things that you can read in this on the screen, you know, where your gender identity, your sexual orientation, your nationality, your ethnicity, your marital status, your socioeconomic background, your anything, wherever you're coming from, this place is for you. You are supposed to be safe here and to be able to learn, because that's what we're supposed to do here. Learn astronomy, learn physics, learn science, right? So if there's anything, you know, nobody is perfect. So TAs and myself, maybe sometimes we'll say stupid things. Please call us on that, you know, please tell us, let us know if there's anything that doesn't make this place welcoming. Or if you think of ways in which we can make this place more inclusive. So I just wanted to make it very clear that I'm very open to comments and to suggestions. So let me leave that behind and go on to our class. So let me look at your questions very quickly. So for people who are here today and that you weren't able to come last Friday. So first of all, my apologies for that. The problem has been fixed, I believe. But the lecture is recorded and it's posted on YouTube, and you can find the link on iLearn. So please go ahead and watch it. You can watch it at 2 times the speed so that you can get through it very quickly. But I did give a lot of important information about the class, so please do go ahead and catch up with that. Do you need to take notes? Yes, of course. You should always take notes. Taking notes makes it much easier to understand things, to retain, et cetera, and the syllabus can be found on iLearn. I know that a lot of you are not familiar with iLearn. There's a lot of first years here, and please, I will ask you to keep yourselves muted. So yes, so iLearn, go to ilearn.ucr.edu, log in, then you'll be able to click on this class. And then there is a button that says syllabus. So just click on that and download it. Same thing with your homework. You'll go to homework, click on it and download it. And let me know if you have trouble. The slides here are posted already on iLearn, so you can download them. They're on a button that says lecture slides. And this lecture is being recorded and I will post it on YouTube. And by the way, in case you have any privacy concerns, so the lectures that I post on YouTube are unlisted. People cannot search for them and find them. You can only get to them through the link that I posted on iLearn and that I sent to you on email. So I sent you the link to the playlist. You can click on that and then you will see all of the lectures as I post them. I also trim the lectures so that all the stuff before the lecture and all the stuff after the lecture is done, I cut it out so that when people ask me questions one-on-one, they will not be on the recording. So, if you choose to unmute yourself at the end of the lecture and talk to me or show your face, on the camera, that's not going to be posted on YouTube. And again, only people with the link will be able to watch it. So just in case you have concerns about your privacy. Yes, the slides are posted. Okay, all right. So let's get to the material for today. And let's talk about some definitions. So these are very basic. You might roll your eyes, but I just want us all to be on the same page. So the first definition is speed. right? So things in the universe move, and they will move with a certain speed, and even light travels with a certain speed. So we will be talking about speed. So let's just make sure we all understand what that means. That is just the rate at which an object moves. And so it is just how much distance it travels in a given amount of time. So for that, the units are usually distance over time. So for example, you see a sign that says speed limit 65, it's 65 miles per hour. You can travel 65 miles in 1 hour. So that's speed. We're all familiar with that. Velocity is like speed, but it has one more component. It's the speed at which an object is going, but in a certain direction. You have to say in what direction. So for example, you're moving 65 miles an hour towards the west, right? Like you're going to LA. So you have to say in which direction. So you can keep your speed constant, but if you turn and you go to a new direction, then you're actually changing your velocity, even if the speed is still the same. So the next definition is acceleration. And acceleration, we're very familiar with this term when it means going faster, right? Like you want to buy a car and you want one that has really good acceleration, right? Where you can go from 0 to 100 miles an hour in like however many seconds. So yeah, that is acceleration. But there are other things that are acceleration too. For example, it's whenever the velocity changes. So like I was saying, you can stay at a constant speed, but if you change the direction, you're changing the velocity, which means you are accelerating. This is counterintuitive. If you're going at a constant speed and then you slow down, if you brake, then that's also an acceleration. So for those of you who are in CNAS or in BCOE and you like vectors, this little movie here shows you you can see how the arrows are representing acceleration and velocity, and you can see how there is an acceleration whenever there is a turn. So whenever the green arrow shows up, that means there's an acceleration, and it can be when you turn, when you slow down, when you speed up. Any of those causes an acceleration. All of these things will be very important in the universe because, like I said, everything is in motion in the universe. So we will be talking about these things. So let me just again show you an acceleration can be when you're going from slower to faster. It can be when you're turning, even if you keep the same speed. Or it can be when you're going from faster to slower. Any of those can be an acceleration. So somebody's asking me about units. Should you use SI units or the units? It will not be as important. I will usually tell you which units. And since I'm not going to make you do calculations, it's not as important. So don't be scared. Sometimes I will talk about kilometers per hour. Sometimes I will talk about miles an hour. But most of the times I will be talking about things that are much bigger, like light years, right? So yeah, don't worry about the units for now. All right, so let me start with a poll now, just to test your knowledge. And let me launch this. So the question is, which of the following have the ability to accelerate a car? And you need to check all that applies. So let me launch this poll. And so it'll just give you A, B, C, D, or E. So hopefully, I think those of you who are using a phone to see the lecture, you might not be able to see the slide and look at the poll at the same time. So maybe I will read them to you. So A is the gas pedal, B is the brakes, C is the steering wheel, D is the speedometer, and E is the gas gauge. And the question was, which of the following have the ability to accelerate the car? Check all that apply. All right. Oh, what's a gas gauge? That's what tells you how much gas you have. That's answer E. All right, so let me end the poll and let's see what people said. So almost everyone said the gas pedal. That's A. So that's true. The gas pedal is allows you to go faster. A lot of you said the brakes. Very good. Good job. Because the brakes will allow you to change the speed. Remember, I mean, you can be going very fast. You step on the brake, you'll go slower. That's an acceleration. C, the steering wheel. Very good. 64% of you got that. So you will change the direction at which you're going. The last two were just distractors. You know, the speedometer tells you how fast you are, so that can't change. Doesn't have the ability to change the acceleration, and the gas gauge, which is what tells you how much gas you have, that also cannot change the acceleration. Very good. All right, so let's talk about forces. That's another thing that we will be talking about again and again in this class. Question, was steering wheel an option? Yes, number 3 was steering wheel was an option, and that can change the acceleration because you can turn, and so you're changing the direction even if you're staying at the same speed, and that is an acceleration. Very good. All right, so a force, we will talk about 4 different types of forces in this class, but in general, a force, whichever type it is, can change the motion of an object. So let me introduce another concept, momentum. So momentum, you may have heard about this in high school, or maybe you've just heard it in common everyday talk, right? When people say, oh, I don't want to lose the momentum. And you have the idea that it's this thing that has to do with motion. But in fact, it has to do not just with motion, it has to do with mass and velocity. So mass is just the stuff that you have, like matter, right? Like what you're made of, or what my glass is made of. It's the amount of matter, right? So my mass times my velocity gives me my momentum. Right now, my momentum is 0, because even though I have mass, I'm not moving, my velocity is 0. So my momentum right now is 0. If I start walking, my momentum will increase. And if I go faster and faster, my momentum will also increase. Now, let's say that I'm walking for a very long time. Like I don't know if you guys saw that movie, Forrest Gump, right? Forrest Gump was running for days and days and days. And let's say that Forrest Gump didn't eat at all. So as Forrest Gump is running, even if he's going at a constant velocity, if he is losing weight, his momentum is going to be decreasing, because momentum is the product of mass times velocity. Or let's say I'm running or walking, a little easier, and then you, I don't know, throw me a ball and I catch it and I keep walking with the same velocity. Well, my momentum has increased, because now all of a sudden I have more mass. I'm carrying something that you threw at me. So my momentum can change, or the momentum of an object can change if its mass changes or if its velocity changes. Normally, it is the velocity that changes, right? You don't wait long enough for Forrest Gump to lose some pounds. So a force, right, since we're talking about forces, a force is anything that can change the momentum of an object. So force is anything that can cause a change in an object's momentum. I think I said velocity, sorry, I meant momentum. Let me read a couple of your questions, guys. We will not be working with free body diagrams. That's in your physics classes. And the momentum, is it relative to whichever frame of reference is chosen? So the answer is yes, but that will not mean anything to most of you until we talk about relativity. We will talk about that, but we'll get to that. Let me just carry on. So if a force can change the momentum of an object, what it means is that a force can affect the mass times velocity of an object. Now, like I said, usually mass doesn't change, right? Usually, I mean, it changed, I mean, yeah, usually, I mean, if I'm walking, my mass is not, like I'm not suddenly getting heavier and lighter. So usually when a force is applied to an object, what it changes is the velocity. So if a force can change the velocity of an object, then what is it that a force causes? And then let me ask you that. So when applied to an object, a force causes, and I give you 4 options. And no, that's not what I want to do. Hold on, give me a second. Nope. Sorry about that. I'm having technical difficulties. Okay, pulse, here we go. So let me. It's not letting me. It's not letting me send. Okay, let me try this. Okay. All right, so when applied to an object, a force causes A, velocity, B, an acceleration, C, a mass, or D, a spin. When applied to an object, a force can cause A, a velocity, B, an acceleration, C, a mass. Oh, no, you're not supposed to do that, dear. Disable annotation for others. Okay. And D spin. All right. So let me end the poll and share the results. So that's correct. When applied to an object, a force causes an acceleration. That's right. This will be very relevant because of the next slide, which will tell us about the force that we will be talking about the most in this class. So in this class, we'll be talking about, this is the one subject, the one thing that we will be talking about the most, which is gravity. So I told you there are 4 different types of forces in the universe. We will cover all 4 of them in this class, but the one that we will be talking about for 95% of the time is the force of gravity. So gravity, just like the movie. Okay, so I'll get to your questions at the end because you're asking very specific things about gravity. So let me tell you in very generic terms, just without getting into very advanced physics about gravity. Gravity is just an attractive force. It's a force that acts between any 2 or more masses. So anytime that anything has mass or matter, right, stuff, there is this attractive force of gravity. And there's two factors that affect the gravitational attraction between those two objects. One of them is mass, the other one is distance. So force of gravity acts between all objects, right? Between the one that we feel the most is between us and our planet, Earth, right? So it attracts us. That's why when we jump, we fall back down because the force of gravity is attracting us. But in reality, I am attracting my computer that is in front of me, and my computer is attracting me. It's just that it's much, much smaller. The force is much smaller. So it depends on two things, right? One is mass. So if there is more mass, then there is more gravity. If the mass increases between two objects, if the mass increases, in the objects, then the force of gravity increases. If the Earth were more massive, we would feel heavier. We would be attracted even more toward Earth. If the Earth were lighter, we would kind of float, right? Like we would be able to jump up and down because we would feel less gravity. The other thing that affects gravity is distance. So if you're closer to the other object, then the force of gravity increases. If you're farther away, then the force of gravity decreases, right? So the farther away, for example, our planet, Earth, is going around the sun because we, the Earth, feel the gravitational pull of the sun. But if we were in Jupiter, which is farther away, then we would feel that gravity from the sun less. So in fact, Jupiter goes around the sun a lot slower than the Earth because that pull is a lot less. So mass and distance is what's so important. If I put it in terms of equations, then this is what it looks like, but I promised we wouldn't do math, so I keep my promise. But I know that some of you are familiar with this equation. And what I want you to get out of this is not that you memorize the formula or whatever, but or that you learn how to plug in numbers. What I want you to see is it just tells you that the force of gravity is equal to some constant, doesn't matter what, but it's the product of the two masses, right? Mass 1 and mass 2 divided by the distance. And for those of you who are mathematically inclined, you'll see immediately that the bigger the distance, the d or the r or whatever the textbook says, the bigger this is, it's a bigger denominator. So you're dividing by a bigger number, which means the force of gravity is going to be smaller. But if they're closer together, then that d is a smaller number, and it's squared, right? That's important. So then the force of gravity will increase more and more. And so it's not so much the formula that I want you to remember, but it is the concept that force of gravity decreases with distance very quickly. That's what this little 2 is, right? It's distance times distance. It's distance squared. So as the two objects go farther and farther, the force of gravity decreases, and we say this, right, exponentially. That's what this exponent means. And you know it intuitive that when we say decreases exponentially, it means it decreases very quickly. Whereas with mass, it increases with more mass, it decreases with less mass. So just think about it. You will be using this over and over again. Again, not as a math problem, but as a concept. We will be using this over and over again. The more mass, the more gravity. The less mass, the less gravity. The more distant, the less gravity. The closer we are, the more gravity. And we'll talk about gravity when we talk about how planets form, when we talk about how the sun produces its energy, when we talk about black holes and how stars explode and the Big Bang. I mean, with everything, we will be coming back to gravity over and over again. Okay. Okay, I'm looking at your questions. So about memorizing this formula, yes and no. So let me tell you, for some of you like formulas, and so then yes, please memorize it. Some of you don't like formulas, so then just learn what it means. And let me give you an example of something that that I could ask, but I probably won't. But here is a poll. So if the distance between two objects is doubled, right? Like you bring them farther away by twice the distance, you double the distance, then the force of gravity between them, how would it change? Would it also go up? You know, it would also be twice as big? Or does it decrease, you know, by a factor of 2? Does it decrease by a factor of 4? Like, does it decrease a lot? Or does it increase a lot by a factor of 4? So let me launch this poll. Choose your answer. And let me. I don't know why it's doing this. Okay, it's gonna have 5 answers. So sorry about that, but here we go. But there's only 4, right, that I have. So does it increase by a lot? Does it increase by a little? Does it increase by a lot? Does it decrease by a little? Does it decrease by a lot? Okay. All right, let me share the results. So I'm glad that the majority of you know that if you put 2 objects farther away from each other, the force of gravity decreases. They will feel less gravity. But then it's a split as to by how much. The answer is by a factor of 4. So what was that? C was the right answer. It's by a factor of 4 because of that d squared. I used to ask these questions a lot in the midterm, and then I realized people kind of struggle with them. So I that's why I said I probably will not ask. What I want you to understand is something most of you have understood already. With bigger distance, the gravity drops. But also remember, it drops very quickly. And just to give you a preview of things that we will learn later, our galaxy has a gigantic black hole in the center of the galaxy. And we don't have to worry about it. It's not going to devour us. We're not going to suddenly fall into it because we're very far away from it. And the force of gravity, even though that black hole has a huge force of gravity, we are so far away and the gravity drops so much that it doesn't affect us at all. So, you know, we'll talk about stuff like that. This is what I want you to get out of this, right? So if we go back to this is what I want you to get out of this. When you have more mass, then the force of gravity becomes stronger. And when you have bigger distances, then the force of gravity decreases. When you have smaller distances, the force of gravity increases. So just think about this. So if you're mathematically oriented, memorize the formula. But if you're not, then this is what I want you to know and understand. And to confirm, C was the correct answer. Okay, so I'm getting a lot of questions. And, you know, just, what time is it? We have 15 minutes. We're going pretty slowly, but it's okay. let me see which ones do I want to answer. So there's a lot of questions about gravity and why gravity, and I love that you're asking that. Unfortunately, we don't have time to answer because there's no good answer. So let me just give you very quickly a historical perspective. So Newton was the first one, Isaac Newton, right? You can look him up, and he was the first one who formulated this whole idea of the force of gravity, right? So here. And so Isaac Newton was the first one who kind of understood that the gravity, the force of gravity or gravity, is an attraction between objects that have mass, and it depends on the distance. So he came up with this formula, and it turns out it's a very accurate formula. And it works for a lot of things, like to calculate, how the planets move around the sun, and also things like how massive our galaxy is, and just simple things like when you throw a baseball, if you take into account things like friction and all that, you can figure out, the path that the baseball is going to take because this formula of gravity works. But that's different from actually understanding what gravity is. And one of your questions was asking, like, well, why does it depend on mass and distance? And why not about on other things? We don't know. We've been trying to figure this out for centuries, right? And we will talk about Einstein. Albert Einstein came up with a very different view of gravity. Gravity is something that bends the universe. And we'll talk a lot more about that. And it works, and it works better. It actually works better than Newtonian, than this formula. But even then, like the philosophical question of why, that I cannot answer. You have to talk to your friends who are taking philosophy, and even them, they can philosophize about it, but it just is. That's the way the universe is. That's the way it works, and that's what we were given, right? I mean, that's like in the Frodo, Lord of the Rings. Like that's what we were given. Anyways, I should know my movies better before I quote them. Okay, so your questions about black holes and all that, I will answer later. Okay, all right, so just a few more definitions and we will, okay, 12 more minutes we have. So let me just, we've been talking about mass, right? But what you talk about in everyday life is weight. Like, how much do you weigh? I need to lose some weight, or I need to gain some weight, not mass. We don't usually talk about mass. Well, what's the difference between those two? Mass is the amount of matter that an object has. And that doesn't change. You can be on Earth, Mars, Jupiter, the moon, in space. You still have the same amount of matter. Weight, on the other hand, is a measurement of the force which acts upon an object. And in most cases, the force that we're talking about is the force of gravity. So weight is how hard the Earth is pulling on us, given the amount of mass that we have. So whereas mass is constant no matter what, weight can actually change. So you guys you've heard about how you weigh less when you are on the moon, because on Earth, when you stand on a scale, the scale is measuring basically how hard you're pushing against the springs, right? It's a force. So your weight might be 200 pounds on Earth, because there is large gravity on Earth. But then you go to the moon, which is a lot lighter than Earth. So it has less mass, it's a lot smaller. So then the gravity is less, and then your weight might go down to 33.2 pounds, right, in this case. So, and that's why you see videos of the astronauts like sort of jumping around the moon, because they feel so light. because the gravity is less. However, your mass doesn't change. You still have the same amount of, muscle and fat and bones and everything else that we're made of. It doesn't matter whether you go to the moon or Earth or wherever. Yeah, so I'm getting a question. So is this why we feel lighter in water? Exactly, because, well, I mean, it's a little more complicated. In water, you have forces of buoyancy. So the water is actually pushing you up. And so that kind of helps counterbalance the force of gravity that is pushing you down. So yes, that's an example. Another example, you're in an elevator and the elevator starts going up. And so the floor of the elevator is going to push harder on your feet, right? So there's more force. It's an acceleration, right? Because the elevator starts to go fast up. And so then you feel a greater force and then you become heavier. Your weight changes, but your mass didn't change. Your mass is exactly the same. You have the same amount of stuff. And then as the elevator slows down, gets to the top floor, right? Maybe you guys did this when you were kids, or maybe you still do it. When it starts to decelerate or accelerate in a negative direction, then you jump because you feel a lot lighter. And so it is the measurement of the force that is acting on you. That's what changes your weight, but your mass is the same. So I was going to do a poll, but actually we're going so fast that I'm just going to give you the answer, right? So on the moon, my weight is the same, but my mass is less. My weight is less, but my mass is the same. That's the right answer, right? On the moon, my weight is less because the force of gravity of the moon is less, but my mass stays the same. My mass stays the same everywhere. And the only thing that can make me change my mass is if I eat a lot of pizzas right now, then I'll have more mass. Okay. Or, if I stop eating for a week, and then I'll have less mass. But otherwise, my mass is the same. Let me that. Okay. All right. Okay, so I'm going to skip this. You can, this is just a demo that shows you how your weight changes in an elevator, but you can go yourselves later. All right, so gravity is a force. Forces can cause accelerations. So the force of gravity from the Earth is always can cause accelerations. And so you know that if you drop something, you have a pen in this case, and you drop it, you know that it's going to fall. But also, it starts to fall at a certain speed, but as time goes on, that speed starts to get faster and faster, right? So it causes an acceleration because forces cause acceleration, right? So recall that forces cause masses to accelerate, meaning forces change the momentum. So as an object falls, then it accelerates because of the force of gravity. And the higher that you drop the ball from, the greater the velocity when it lands. And that's an acceleration. So I'm going to, yeah, so I'm, I'm going to change I'm just going to change it so that everyone is muted, but you guys, please mute yourselves. So anyways, thank you. Okay, so you drop a ball from a building, and after the first second, it's going to reach a certain speed, 10 meters per second. After the second, it's going to be going even faster. It's a constant acceleration. Every second, the velocity will increase by about the same amount. So it gets faster and faster. And you know this intuitively, right? You would jump off, the top of a desk. You can stand on a desk and jump down, and you know that nothing is going to happen. But you know that if you go much higher up, if you go to the top of a building, you're not gonna do very well if you jump off, because you're probably going to hit the ground so fast that your bones are probably going to crack, and you might die. So you don't do that, and this intuitive, and that's why it's because gravity, the force of gravity, causes an acceleration, which means you get the longer you fall, right? The farther away from the ground you jump, the faster you're going to be going when you hit the ground. Okay, so terminal velocities, yes. So some people are asking about terminal velocity. That's something when you jump off an airplane, for example, if you're going to be parachuting, you do reach something called a terminal velocity, and that's because of friction with the air, right? So we're not going to talk about that, because most of the time we'll be talking about the universe and places where there's no air, there's no atmosphere, there's nothing that slows you down. So, right. All right, so we have time to just start this, and we will continue next time. So there's 3 laws of motion, Newton's laws of motion, and we'll talk about all 3 of them. We've sort of alluded to all 3 of them already, but here we go. So the first one, I'm going to paraphrase it. You can find it on chapter 3.2 of your textbook, but paraphrasing Newton's laws of motion. So the first one says that an object's momentum does not change if you leave it alone, right? As long as you don't exert a force on an object, the momentum will not change. So an example of that is, I am sitting here and my momentum is 0, and my momentum will continue to be 0 unless you push me, right? Unless someone pushes, and then my momentum will change. But otherwise, it'll just stay the same. This is a nice application for space, because you have a spaceship that is moving, and as long as nothing stops it, and there's no friction, right? There's no friction in space. So as long as nothing stops it, it'll continue to move. The planets are going around the sun. And as long as you don't exert a force, they will continue to go. And this is a nice thing. So something that is not moving will not start moving spontaneously. It needs a force. And something that is moving will not stop moving spontaneously. It needs a force to stop it. The second of Newton's law is exactly what I just said. You can use a force to change the momentum of an object. So an example here that they give is a baseball that accelerates as the pitcher applies a force, by moving their arm. And so then the ball that had a momentum of 0, then you give it a force, and then all of a sudden it has an acceleration. Yes, you do have a textbook for this class, and it's free and it's online, and you can find it on the syllabus. All right, so the third, this is the most confusing one. And I will start with that next time, because I see that it's pretty late. So, but let me just state it. For any force, there is always an equal and opposite reaction force. And I like to restate this in terms of momentum. And I like to say momentum is always conserved. So the example that people like to give is a rocket. In the case of a rocket, the fuel is pushing down. So there's gas that is escaping down at a very high velocity. And as a reaction, the rocket goes in the opposite direction. But I will talk about this in more detail, because it's the more confusing one, as I said. So I will start with that next time, so on Wednesday. It looks like everyone was able to come to lecture and we don't need to do the YouTube thing next time. So, so anyways, I will see you guys on Wednesday. You're more than welcome to stay behind and ask questions. And I will also answer some of the questions that you guys asked on the chat. So I will see you later. See you on Wednesday. So let me bring the chat.
Goodbye.
Bye-bye. Thank you for the class.
Thank you.
And let me stop recording. Stop
Bye. Thank
recording.
you.